Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 9. In this lecture, we'll discuss simple waves. This topic is covered in Chapter 16 of our textbook by Surway and Jouet. In our previous lecture, we provided a qualitative description of waves. It's now time to turn to a more precise quantitative description of waves. In general, waves can be very complicated to describe, but it turns out that all waves can be described in terms of simple waves. You can think of simple waves, which are also known as sinusoidal waves, as the building blocks of more complicated waves. So one can combine multiple simple waves together to create more complex, more interesting waves. A simple wave is described by the following function. When describing rope waves, we use the letter Y to describe the wave, although one may use other letters as well. Later on, when we talk about sound waves, we'll describe the wave function using the letter S. And sometimes when we're speaking of waves more generally, we'll just use the letter W to denote the wave. The wave function will depend on at least two variables, x and t. T, of course, is time, and x represents position along the rope. So you might be interested in the vertical displacement of an atom of the rope that is located, let's say 2.5 meters along the length of the rope. In that case, x would be 2.5. If you're interested in the vertical displacement of a different atom located 3 meters along the length, then x would be 3. This function is going to be equal to a sine of this very complicated argument. You should already be familiar with a as the amplitude. It's the same amplitude that we encountered when discussing simple harmonic motion. This parameter here is the Greek letter lambda, which denotes wavelength. The wavelength tells us the distance between two peaks of the wave. It essentially describes the distance between two atoms that are doing exactly the same thing along the length of the rope. They must have the same displacement and the same velocity. If you were to make a graph of y versus x, then the distance between two peaks on that graph would correspond to the wavelength. We also have capital T. Capital T refers to the period of the wave. It's also the time between two peaks, but on a different graph. Notice that now we have a function that depends on x and t. So we can create graphs of y versus x and y versus t. When we create a graph of y versus t, on that graph, the distance between two peaks will be referred to as the period. The period is the amount of time it takes for one atom or molecule of the rope to complete a cycle of its oscillation. Another parameter that you should already be familiar with is phi, the phase constant, and this indicates the starting point of the wave. If you are holding one end of a rope and you want to generate waves, you have some options in how you start that wave. You can move your hand upwards, for example, to start the waves, but you can also move your hand downwards. You could start at the equilibrium, or you can start above the equilibrium. So phi corresponds to that starting point. Given the starting point or the initial position of the wave, we can calculate phi. Note that in this function, we have a plus and minus separating the position and the time terms. The plus or minus determines the direction of propagation. If you're looking at waves along a rope, those waves could be propagating from left to right, but they can also be propagating from right to left. Those two different propagation directions correspond to these two different signs. A little more precisely, when you have a plus sign here, you have a wave that is moving in the negative x direction. But if you have a negative sign here in this function, then you have a wave that is moving in the positive x direction. So the association between direction and the sign is a little bit counterintuitive. At this point, it is not at all obvious why the plus sign corresponds to the negative direction. We'll appreciate that fact a little more later on when we have a better understanding of waves. In most elementary applications, a simple wave is described by this function on top. However, in slightly more advanced applications, you'll sometimes see the same function written in this form. Comparing the two lines, you can clearly see that 2 pi over lambda has been replaced by k, and 2 pi over t has been replaced by omega. K is a new parameter in the context of waves. K is referred to as the wave number. It is simply defined as 2 pi over lambda. Do not confuse the wave number with the spring constant, which we encountered in our discussions of the mass spring system. The wave number tells us how many radians the wave goes through in each meter of distance, or in each meter along the length of the rope. Omega is referred to as angular frequency. You should already be familiar with this from our discussions of simple harmonic motion. It is defined as 2 pi over the period. It tells us the number of radians that the wave goes through per second. Notice the wave number and the angular frequency measure very similar things. One of them measures the number of radians per meter, the other one radians per second. So one of them is referring to distance and the other one is referring to time. And of course, related to angular frequency is just regular frequency, f, which is simply omega divided by 2 pi. Waves appear in many different contexts and many different applications. So it shouldn't be too surprising to see the simple wave function described in several different forms. A third form that we will often use to describe the same function is this form down here. What's new in this equation is the parameter v. V refers to the wave speed. It is the speed with which energy travels along the length of the rope. Note that wave speed is not the speed with which individual atoms or molecules move up and down. Wave speed describes the speed with which energy travels from one end of the rope to the other end of the rope. If you compare this second equation to the third equation, you will see that the wave speed was obtained by essentially factoring out k from this portion of the argument of the sine function. So the wave speed can be expressed as omega over k. The ratio of angular frequency to wave number gives us the speed with which energy is traveling along the length of the rope. Also recall from the previous slide that omega can be expressed as 2 pi over the period, and the wave number can be expressed as 2 pi over the wavelength. Taking these two expressions and substituting them in for omega and k, we find that the wave speed can also be described as the ratio of lambda to t. So the ratio of wavelength to period also gives us the wave speed. This should make sense. What this equation is telling us is that the wave speed is the ratio of the length of one wave to the period or amount of time it takes for that wave or cycle to complete itself. This quantity also has the right units. Wavelength is measured in meters and period is measured in seconds, so wave speed is measured in meters per second as one would expect. So let's do a practice problem to help us process some of the information we've seen so far. Suppose you notice water waves traveling on the surface of a swimming pool that is 20 meters in length. At one instant, you count 5 complete wavelengths on the surface. When you track one of the peaks, it takes 2 seconds to travel the full length of the pool. The vertical distance between a valley and a peak is 0.2 meters. write a wave function that describes these waves. So here I'm providing you with a verbal description of water waves, and I want you to give me a precise mathematical description in terms of a function. It helps to have a picture in mind. Here is what the surface of the swimming pool might look like. The swimming pool is 20 meters in length. And we are told that we can see 5 complete wavelengths on the surface. So if you look at these waves here, you will see 5 peaks. Here is one complete wavelength. Here's a second one. Here's a third complete wavelength, and a fourth and a fifth complete wave. The vertical distance between a peak and a valley is 0.2 meters. This is an important piece of information because it basically tells us that the amplitude is 0.1 meter. Remember that the amplitude of the wave is the vertical distance from the peak to the equilibrium point, or this middle point here. So if the distance from a peak to a valley is 0.2, then the amplitude is going to be half of that, which is 0.1 meter. We also need to calculate other parameters of the wave. We notice that we're told there are 5 complete wavelengths along the length of the pool. If you can fit 5 waves along 20 meters, then each one of those waves must be 4 meters long. So you can take the length of the swimming pool and divide it by the number of complete wavelengths, and you get lambda. So lambda is 4 meters. We also notice that it takes 2 seconds to travel the full length of the pool. So it takes each one of these peaks 2 seconds to travel 20 meters. If an object travels 20 meters in 2 seconds, then its speed must be 10 meters per second. Here, we're basically using a concept that you probably encountered back in your mechanics course. In your mechanics course, you learned that if an object travels some distance, let's call it delta x, in some time delta t, then the ratio of distance to time is basically the speed of that object in meters per second. So here what we're finding is that the speed of the waves is simply 10 meters per second. This is important because it allows us to figure out the period of the waves. Remember that wave speed is wavelength divided by period. Rearranging that equation, we find that the period is lambda over v, or 4 meters divided by 10 meters per second, which I can express as 2/5 of a second. I'm now ready to write down the precise mathematical function. Remember that one way to describe simple waves is using this function here. We now know that A is 0.1. We know lambda is 4 meters, so 2 pi over 4 simply gives me pi over 2 times x. We know that t, the period, is 2/5 of a second. If I substitute that in here, what I'll get is 5 pi times t. And in this case, we're assuming that the waves simply start at equilibrium, and so we're going to set phi equal to 0, although technically that information is not really provided in the problem. Also, we don't know if these waves are moving to the left or to the right. If they were moving to the right, if that information was given to us, then we would choose the negative sign. If these waves are moving to the left, that is in the negative x direction, then we would choose the positive sign. In discussing waves, it's often helpful to have graphs of waves to help us visualize the waves, the behavior of the medium. However, you should remember that graphing waves is a little bit trickier because a wave function depends on 2 independent variables. So if we're talking about the motion of a rope wave, for example, we describe the displacement using the letter y, which tells us that each individual atom is moving in the y direction along one dimension. So we describe that as a one-dimensional wave. However, That function depends on two independent variables, x and t. What that means is that if we were to make a graph of this function, what we would really have is a three-dimensional graph, something that is better described as a surface plot. We call this a three-dimensional graph because one axis corresponds to the independent variable x, the other axis corresponds to the independent variable t, and the third axis corresponds to the dependent variable y. So y must depend on both x and t. This surface plot that you see here is a plot of this function here. It's a complete description of what a rope wave is doing at any particular time. If you rotate the same graph and orient it so that the x-axis is horizontal like this, then you can basically see what snapshots or pictures of the wave would look like at different times. So each one of these lines or each cross-section of this surface would give us a picture of the wave at particular times along its evolution. We're not going to use surface plots like this very often because they're difficult to generate or draw. However, keep in mind that we are talking about a more complicated situation compared to simple harmonic motion. We have a function y, which now depends on two independent variables. So let's end this lecture with a practice problem. Two snapshots of a wave along a rope are provided as shown below. Find y of x and t. So we're talking about waves propagating along a stretch of rope, and what we have here are two snapshots or two pictures of the rope. At t equals 0, we have one snapshot of the rope. The rope at that moment in time looks like this function on the left. 3 seconds later, we take another picture of the rope, and the wave has changed a little bit, and now the rope looks like this function on the right. Based on this information, can you write down the precise mathematical function for this wave? Now, much of the information that we need to write down the function is not explicitly provided to us. Remember that we need to calculate things like the amplitude, the phase constant, the wavelength, and the period of the wave. So we have to calculate these different parameters indirectly based on these two snapshots. First of all, notice that the two graphs that you see here are graphs of y versus x, not graphs of y versus t. One could also talk about graphs of y versus t. Those graphs would provide different information. These graphs provide information about the wavelength of the wave. Notice that the wave starts at 0 at its equilibrium value. It increases and then it decreases. It completes a cycle just like a sine function, like an ordinary sine function with a phase constant of 0. Also notice that we're not given very many numbers, but we are told that 1/4 of a wavelength is equal to 4 meters. Remember that one complete wavelength of a sine function would start here and it would continue all the way over here. So what we can say is that this distance from here to here is one full wavelength. And this 4 meters here is really 1/4 of a full wavelength, which tells us that a wavelength must be 16 meters. So what we're saying is that if from here to a peak, which is just 1/4 of a wavelength is 4 meters, completing an entire wavelength would require 16 meters. So that's one bit of useful information. Next, we will turn to speed. Turns out we can calculate the wave speed by comparing these two graphs. Remember that on the left, we're essentially looking at the wave at t equals 0. So we could say that this particular peak at this particular time has an x coordinate of 4. Now the wave is moving. Let's pretend like it's moving to the right, in which case you can see that 3 seconds later, that same peak is located at x equals 5. the wave has moved. That's what waves do. They propagate along the length of the rope. In this particular case, the peak has moved 1 meter from 4 to 5, and it has done so in 3 seconds, from 0 to 3. That allows us to figure out the wave speed. The wave speed is 1/3 of a meter per second, or 1 meter in 3 seconds. Now that we have the wavelength and the wave speed, we can figure out the period. Remember that the wave speed is really lambda divided by t. By rearranging that equation, we find that the period is lambda over v, or 16 meters divided by 1/3, which gives us 48 seconds. Now that we have lambda and t, we can finally write down a precise function. We can say that y as a function of x and t is equal to the amplitude, which is 3. We read that off from the graph. As you can see, the maximum displacement is simply 3 meters, times the sine function. Then we have 2 pi over lambda, which we decided is 16. We've chosen the minus sign here because we think the wave is moving to the right. And then we have 2 pi over the period, which is 48 seconds. And we've chosen phi to be 0 because in this case, the function starts at 0. And that is the end of this lecture. Thank you for your attention.